Good afternoon, everyone. I am Adrian Cahlil East Togonon, and I'm here to present the Smart iLab project headed by Dr. JB de Guzman and donated by UPERDFI. For the outline of our presentation, we'll be first introducing the Smart iLab and its three main features, namely teleconferencing, IoT, and renewable energy. We first start with the teleconferencing setup of the Smart iLab and our mirrored lab setup. Next, we will talk about our IoT systems to create our IoT testbed platform. Then we'll briefly discuss our underlying infrastructure, and finally, the renewable solar energy system to power the classroom. So what is Smart iLab? Short for Smart Instructional Laboratory, it is a project that aims to redesign a laboratory in EEI. The room will be IoT-driven with sensing and automation features and equipped with solar energy to power the whole room. We also designed a teleconference setup for hybrid learning where we aim to extend the scope of course delivery in EEI. First, let's start with our designed teleconferencing setup. So the main goal of our teleconferencing setup is to extend laboratory courses outside Smart iLab. The recent pandemic has shown us the importance of remote or hybrid learning setups, but we want to enhance the functionality so we can extend course delivery to other rooms in EEI if there's not enough space in the room. Another use case is to extend course delivery to other state university colleges that previously may not be able to host such a course. As Zoom is the most commonly used platform in the Institute, our system is mainly designed to facilitate remote learning and lab mirroring through Zoom. Other requirements that we identified is the ease of use, even for non-technical faculty or staff, which can be achieved with a plug-and-play system. With those requirements, here is our designed teleconferencing setup for the Smart iLab. The star of the show is an interactive flat panel with built-in whiteboard and content sharing features. We identified that 2 cameras, one for the lecturer and one for the audience, is needed to simulate an extended classroom feel. The cameras we use have auto-tracking features for an operator-free experience when lecturing. We also deployed a wireless conferencing hub called Barco ClickShare, where with just a USB-C dongle and a click of a button, you can share content to the screens from anywhere in the room. Both the interactive flat panel and the Barco act as a USB hub where you can access all of the peripherals with a single cable. For the mirrored setup, we have chosen the Department of Electrical Engineering in UP Los Baños as a pilot deployment. The setup we designed is very similar, with the only difference being a smaller interactive screen, no wireless conferencing hub, and a different PTZ camera. We will complement their current setup, where they have TVs, soundbars, and camera from the Picari Prime project, which will serve as our back TV setup. If you noticed from the 2 setups, we also want a front and a back screen, as well as 2 cameras for the lecturer and the audience always. This is so we can achieve our extended classroom vision, where the host can see who is in the mirrored classroom with the back screen, and the mirrored classroom will see the lecturer in the front screen. This goes both ways, such that either the Smart iLab or UPLB DEE can host each other. With this setup, we can extend or receive courses from other classrooms with a similar setup. Next, we move on to the IoT-driven features of the Smart iLab. This infographic shows all of the IoT services and features of the Smart iLab project. We'll talk about our IoT stack, which will be the backbone of our IoT testbed platform. We have a Smart HVAC system to control the ventilation and AC, the Smart lighting system for personalized lighting and wireless control, and we'll also talk about energy monitoring and at different monitoring levels, then our servers that provide the architecture to host these services. Finally, we will have our solar energy system, which will be powering the Smart iLab. The Smart iLab is supported by several locally hosted IoT services that allow the different systems to integrate and interoperate. Most devices that we use are Wi-Fi or Zigbee-based, so gateways are necessary to interface different communication protocols. We will be discussing these services and features that make them essential for the Smart iLab. Our main system integration platform of choice is Home Assistant, which is primarily used for home automation systems, but we extended its use case to a smart laboratory setting. It has the advantages of being locally hosted to avoid cloud fees and security risks, as well as system control even without internet. Being community-driven and open source, there's a wide range of integrations for many devices and interfaces. It also has a feature such as customizable UN dashboard, automation, scripts, and scenes. For the HVAC control, we opted to use the Sensible Air Pro Air Blaster to control our dome ACs. Sensible is cloud-based, but there is a HomeKit integration in Home Assistant for local control. It is better than regular Air Blasters, where you need to train all remote commands manually, whereas Sensible has built-in climate control already, as shown on the right. For the IoT stack, most of our sensors use the ESP Home system to configure ESP-based devices in Home Assistant. It's a simple programming language where you can write configuration files using ESP Home building blocks, which allows for easy-to-build and flash setup of many ESP-based home IoT devices. And here's the overall IoT stack that we are deploying in Smart iLab. We divided the room into 16 different zones for each workstation. Each zone will have their own IoT stack, which includes 2 Atom energy monitoring plugs, 1 Apollo air quality sensor, and 1 Apollo occupancy sensor. The lighting setup will also be divided into these zones for personalization per workstation, where the IoT stack can interact as well. The room also has aggregator 1 air quality sensor and 4 Apollo multi-target tracking sensors. And we also have Emporia View 2s for breaker level monitoring and Sensible Air Pros, which we'll be discussing more in the future. For this occupancy detection, we used a millimeter wave sensors, such as Apollo multi-sensor for each zone and Apollo multi-target sensors for general room occupancy. The MSR2 has 3 different configurable distance zones as well as per gate thresholds. And we chose this over MTR1 that has a relatively new LD2450 sensor, which has poor tracking against multiple targets and worse still detection. Shown here, we also have the specifications for the Apollo air quality sensor, which we deployed for each zone, and the Air Gradient 1 for general room monitoring. And as mentioned, we have smart plugs pre-flashed with ESP Home for workstation monitoring, and Emporia View 2 for breaker level monitoring. For Emporia, we can use the cloud integration to import aggregated data to Home Assistant. Once it is an ESP-based device, we can actually flash it with ESP Home configurations from the internet to get raw power, voltage, and current data. And this has actually been useful for us when we found that the base Emporia configuration only works for electrical systems with line-to-neutral configuration. And we had a problem that the building 1 of triple EI is in a delta configuration with no neutral. So we solved this by flashing a custom ESP Home configuration to derive the line-to-line voltage and get a correct power consumption. However, a limitation is that we cannot get the phase of the AC current from the current clamp. So there is a slight error due to an assumed power factor. Next will be the lighting system that we designed, which features a track-based setup to allow reconfiguration of plug-and-play lights due to the possibility of different room layouts depending on the usage for the semester. We have diffuse lighting for general room lighting and ambience, as well as focused lighting for personalized workstation lighting. Its brightness and color temperature can be adjusted, which allows for productivity research in the future. This lighting system is also Zigbee-based, which we will talk about more later. Here are some of the lighting renders of the 2 layouts where you have the front-facing classroom mode and the laboratory mode that is currently being used in Smart iLab. Our lighting system is based on the Zigbee communication that allows for wireless control and configuration of individual lighting fixtures. Zigbee boasts low power consumption and cost, has high capacity, fast response, and high safety. To integrate Zigbee devices with Home Assistant, we deployed a ZigStar coordinator as a gateway to the devices and a Zigbee to MQTT server to control the devices using the MQTT protocol. And as a background, MQTT is a lightweight publish-subscribe network messaging protocol that is usually used in IoT applications. With its standardized messaging format, it can provide platform-agnostic monitoring and control of IoT devices. It requires an MQTT broker, however, which we deployed an EMKX server in a Docker container, as shown here. One possible issue that can arise, though, is that the coordinator is a single point of failure for controlling devices using Home Assistant. To fix this, Z2M has the functionality of direct binding with the remote to still control the devices even when the servers are down. Another issue is Wi-Fi interference, since ZigBee is a 2.4 GHz channel as well, but this can be resolved with good planning of channel usage. So the long-term goal of the project is to develop an IoT testbed and platform for students to research in the future. The ZigBee Lighting and ESP Home have MQTT integration that can provide platform-agnostic monitoring and control over these devices. A REST API server, or Node-RED, or Home Assistant can be developed to interact with the IoT platform. Research work on the IoT testbed is being performed by an undergraduate student currently called sensor fusion, where you can have air quality and energy consumption to predict occupancy using a Bayesian model. Another use case is an air quality mapping, where you can map air quality across different zones to see how pollutants move in real time. And while Home Assistant has its own database and graphing capabilities, we chose to have an external timescale DB database for storing time series data long term. We experienced data corruption due to power outages before, so we used StackRest to deploy a production-level database in a Kubernetes environment. It has built-in features such as replication, high availability, monitoring, and to prevent total data loss in the future. And StackRest also has a built-in Prometheus and Grafana server to monitor the cluster's health and database usage. Then, to visualize the data from the timescale DB, we use Grafana to show our data in a dashboard, where we can perform data correlation and validation, comparison studies, or just general live monitoring in a presentable format. And finally, we will be talking about the green energy aspect of the Smart iLab, which will be discussed briefly. The Smart iLab will be powered by a 55 kilowatt solar energy system, where the inverters are all grid-tied, since power consumption in EEI is still usually higher than production. There are concerns, however, of overproduction during off hours, in which we have two options. The first option is net metering, but there are permit issues, so we opted for a current limiter system for the SME inverters to automatically limit energy production. The SME inverters we chose also have data monitoring for the solar energy production, which can be accessed through its web UI and can be integrated into Home Assistant as well, as shown in the image here. And by being able to monitor energy consumption and solar energy production, an undergraduate research group was able to research the feasibility of fully powering a classroom with solar energy, as well as performing life cycle cost analysis. The results are shown here, and they found that a 55 kilowatt system can power 4 smart classrooms simultaneously. Through our systems, we were able to enable research in energy monitoring, and hopefully we can enable more research on IoT and smart classrooms in the future. And that concludes my presentation for the Smart iLab project. Thank you, and good afternoon.
Thank you, Sir Adrian. We have time for questions from the audience. Anyone? Ako na naman. Okay, sige, I'll start. So I understand from what I understood is that you're focusing on enhancing the energy efficiency of the laboratory setting. So has this been deployed and used by students, and does it enhance, or is there a way to know if it enhances the collaborative and learning output of the users?
For this teleconferencing setup, we are still in the works we already have bought the items to deploy the teleconferencing setup, and we'll be installing the teleconferencing setup around next month after the installation of lighting fixtures next week. And yeah.
Okay.
We'll be checking the the efficiency of the teleconferencing setup through other means.
Okay. Thank you, Sir Adrian. Any questions from the audience? Yes, sir.
Good. Thank you for your presentation. In terms of the IoT format for energy efficiency, have you already transitioned to a comprehensive Industry 4.0 enabled facility like a laboratory? Is it in the pipeline or is it already existing at the moment?
Sorry, what industry? Can you repeat yung industry
Sorry,
part?
so Industry 4.0 includes 4 major areas. One is IoT, the other one is database, data science management, process, and all the others that are actually connected by an algorithm that's actually what you presented for energy efficiency. There is a movement in the industry wherein the facilities are actually Industry 4.0 enabled already. And there is a huge niche that needs to be filled, particularly here in the Philippines, for that particular directions. So I'm just wondering if it is part of the research pipeline to go to that direction.
We are not that familiar with the Industry 4.0.
Sorry.
I know, but if we can research on the Industry 4.0 and we can see if we can integrate that in our research pipeline.
And yeah, because I'm very interested because I'm in the manufacturing area for molecular diagnostics, and part of the competitiveness in the regional scale is an Industry 4.0 enabled facility. I think previously it's called a digital twin, but now it has evolved into that particular aspect. So listening to your presentation, it felt like you are already fulfilling a quarter of that requirement at the regional level. So I'm quite interested and excited if there are initiatives at the local level to actually do that, because there are industries like us interested to transform our facilities into an I4 enabled facility. And that includes this aspect actually.
Yeah, I think we can integrate that pipeline into our research. Thank you, sir. Any more questions?
Any questions? Okay. So let me present to you your certificate of appreciation. This is presented to Sir Adrian, Cahlil, Togonon for sharing their invaluable insight and work on Smart Instructional Laboratory or Smart iLab, a green, future-ready, and collaborative instructional laboratory for engineering education during the NEECE Con 2024, given this 19th day of July 2024 at Novotel, Manila, Araneta City, Quezon City, Philippines, signed Dr. Lou Andrew Tria.